we're going to start with a just a little bit of a refresher on momentum and momentum conservation. And then, so if you don't have it downloaded yet or open on your computer, you can go to Blackboard and open the momentum tutorial. I think it's called on Blackboard. Download that PDF there so that you have that open to discuss. Zoom used to allow for file sharing, but they've removed that recently for security reasons. So, okay, so let me share the screen and here we go. So, so just a quick refresher on momentum conservation. We generally use this in collisions. So before a collision, in this problem or in this worksheet, after the first page is just kind of a warm up, thinking about momentum of individual objects versus the momentum of a system of two objects. So here we have what the rest of the worksheet's going to look like, and it's one object colliding. We could say elastically, but in reality, it doesn't matter as long as what we care about is momentum, right? So we have one object at rest. It's so object B is always going to start out at rest before the collision. Object A runs into it, and then they collide and have final velocities. So just a momentum, a really simple equation. You just take the mass of the object times its velocity. So both mass and velocity are going to be important as you consider answering these questions. Momentum is always conserved in a collision as long as there's no force from outside the system. So if you get to the final part of the worksheet today, there will be a point where there's some friction involved, and that will change things. Momentum is a vector, so you can't ignore the plus or minus sign, right? So as an example, if you throw a tennis ball at a wall, if it's an elastic collision, because the wall doesn't move, it's basically infinitely massive, the tennis ball will bounce back at the same speed that it hits. But because it changes direction, that's very important. You can't say that the momentum is the same as it was before the collision. It's going to change because the change in signs is very important. Okay, and then because the momentum of the system doesn't change, then if you have a change in momentum for object A, for instance here, that's going to have the same magnitude as the change in collision for object B, but they're going to have opposite signs, right? So if object A has a negative change in momentum, right? So if we look at this collision in this example, that's definitely the case. Even though we don't have numbers, we know that A starts with positive momentum and ends with negative, so its change in momentum is going to be negative. And B starts with 0 momentum and ends with positive, so its change in momentum is going to be positive, right? So they have opposite signs. In the change has opposite signs, but they're going to be equal in magnitude. Should be back now. Okay, so what I'd like to do is to kind of see where everybody is, use the poll everywhere. So if you could pull that up. So that's that link is there, pollev.com/SeanBartz041. And this is the first question of part 2, page 2 of the worksheet. Yes, so the momentum of the glider is actually greater than the momentum of the entire system. So it might seem weird at first, but the reason why this is the case is because before the collision, all the momentum belongs to block A, right? So in the picture or the vectors, it was 5 units of momentum. So afterwards, the total momentum of the system still has to be 5 units, right? And those little arrows, whatever those blocks would represent, you could say, the SI unit is just kilogram meters per second. So after the collision, because A is going to have negative momentum, right? I picked arbitrarily, I said it was -2 units. Then that means to make a total of 5, you'd have to have the momentum of block B be 7 units, right? So B has 7 units, A has -2. That makes a total of 5, which is what we need. And so because the direction matters, an object can have a greater momentum than the total momentum of the system. Right. So this is different from energy, right? When you have energy, if one object sort of gives up some energy, the other object is going to gain that energy. But momentum having direction, an object can give up, in a sense, more than all of its momentum. Right. So A gives object B 7 units of momentum, even though A, in a sense, didn't have that much to give, but that just leaves A with a negative momentum. All right, let me see. Can I go to the next one this way? Yes. Okay. So I don't know how far people got with this part, but let's look at object A. Or sorry, in this case, we have object A always has the same momentum to start, just like we looked at. Basically, we were looking at experiment 1. But what happens if you keep making B have a bigger mass, right? So A starts with some momentum, B has starts at rest, but it keeps getting more and more massive. So if we want to compare the final momentum of B, which one would be the biggest? So would it be the biggest would B's final momentum be the biggest when B is is the least massive? That's option A. Would it be the biggest when B is the most massive? That's option B. Or is it always the same? So I know that you may not have been able to go through all the analysis here, but just give your impression. So showing your first thoughts here that okay, so I mean, we can definitely look at object B, and the arrows in this picture kind of are illustrative, right? In experiment 1, where B is the smallest mass, it's going to have the biggest velocity, and then in experiment 3, where B is the biggest mass, it's going to have the smallest velocity. Now we know that a big mass or a big velocity is a way to get a big momentum. So we have to. The question is whether those things balance each other out, or which one ends up, outweighing the other. So now I want to draw your attention to the velocity vectors on object A. Right. So in experiment 1, object A has kind of a small velocity that's negative, but by the time we get to experiment 3, A has a bigger velocity afterwards, right? So you could think about, if I have a tennis ball and I roll it into, if I make it run into a basketball, the tennis ball is going to bounce back. But if I roll it into a bowling ball, it's probably going to bounce back even faster, right? So the bigger the target is, the object that's rest, the faster the moving object will bounce back. So object A has a bigger change in momentum in the more massive that object B is. And because, oops, I didn't mean to do that. Let's show the correct. So perhaps, well, clearly counterintuitively, since nobody picked this even initially, it's experiment 3, where object B is the most massive, where object B would have the greatest momentum at the end. Right, so it wouldn't look like it because it's not going to be moving very fast, but the mass more than makes up for that. And the only way that we can tell is to say, well, um, object A has the biggest, velocity to the left, and therefore the most negative momentum in experiment 3. And so that means that B needs to gain the most momentum in experiment 3 in order to compensate. All right, so I encourage you, if you didn't get much time to go through the drawing of the arrows in each of those examples, I encourage you to do that. Remember that the systems, in all the cases, the initial system looks the same, right? You've got 5 units of momentum for the system because that's all from object A. So then the first thing that we can do is say, okay, the system is going to have 5 units of momentum in all cases. And as we go, using these arrows, right, that the arrow keeps getting bigger for the velocity, that means that the negative, the left pointing momentum of the of object A keeps getting larger, right? So to keep, so in this case, I had it be -2 in the first experiment. The second experiment, I had it be -3, and in the third experiment, I had it be -4, right? Just to kind of arbitrarily pick and to make sure that my other arrows would all fit in the picture. So that means that in experiment 1, -2 plus 7 is going to add up to -5. Or sorry, +5. In experiment 2, -3 plus 8 has to add up to 5. And in the final experiment, experiment 3, -4 for object A means that object B has to have +9 units of momentum to keep adding up to 5 for the total system. So, it's definitely counterintuitive, but you have to use the fact that the final momentum of the system and that you're given that object A keeps bouncing back with a greater velocity. So, the main thing that I'm looking for you to take from these examples is, one, that direction really matters for velocity, right? So direction, well, it matters for velocity and therefore it matters for momentum, right? And that it's not, I feel like energy conservation is a little bit more intuitive, because you can think about sort of, we looked at those examples where you had the sort of bars, the bar graph of all the energy becomes one type, say potential, and then it all switches back to kinetic and goes back and forth. Whereas momentum, you can go below 0. You can have a negative momentum, and so an object can give up, quote unquote, more than all of its momentum to the other object in a collision if it bounces backwards.